This video picks up from my intro video about dark matter, which is linked here, if you want to check that out. Back then, we established that the amount of mass that we can observe in the universe does not fit to what the stars and galaxies are actually doing, how they're moving. In fact, it looks like less than 20% of the universe's mass is visible to us, and the rest is somehow dark. This left us with two interesting options. Either A, there is a large amount of mass that we can currently not detect, or B, all of our theories are wrong at very large scales. Now, I absolutely will make a video about the second option, but this video will be about the first. Assuming there is invisible mass, what could it be and how could we measure it? There is this impression with many lay people that dark matter is simply something we can't detect and we know nothing about it and we just shrug and move on or wait or whatever. In reality, we've done a lot of observations and experiments in this direction over the last 30 years. Granted, none of which have really been successful, so they either found nothing or rare signals that could not be replicated or confirmed. Why do we keep doing it then? Because sometimes you first have to learn what something isn't to figure out more about what it actually might be. Also, whenever talking about dark matter, there's a lot of people that will immediately go, well, couldn't it just be this or that? And the reason why it could not be is probably in this video. First, let's define precisely what we mean by invisible or dark, because I've always found this to be the most confusing part of the whole discussion and also the most important thing you need to understand about the problem. We look at the universe by capturing light, electromagnetic radiation. This could either be visible light or X-rays or microwaves or infrared. It doesn't really matter. Some objects, like stars, produce their own light using nuclear fusion, while others, like gas clouds or planets, simply reflect this light or absorb it and later re-emit it. Everything emitting light is in principle visible to us. However, it might be too dim or too far away, and this would also count as invisible here. And, pretty much by definition, any objects which don't interact with light at all are also invisible. Given just that, we can already rule out a lot of astronomical objects as candidates for dark matter. It can't be atomic or molecular gas clouds, because those would absorb and emit light. For example, the strong hydrogen 21 centimeter line. At the very least, it would absorb or scatter background radiation, so it would be clearly visible to us. And the same goes for dust clouds, which would emit in infrared. Also, that much dust would require much more heavy elements than there should be, as all our cosmological evidence strongly points at a preponderance of light elements, around 75% hydrogen and almost the entire rest helium. Now, kinda obviously, it could also not be normal stars or similar objects, as these are bright and clearly visible. And this leaves broadly two possible categories of what dark matter could be. Either large astronomical objects, similar to stars but too faint to see, or a large number of microscopic particles spread out all over space, which don't interact with light at all. Now, for unfortunate historical reasons, these are called MACHOs and WIMPs. MACHO is an abbreviation for massive compact halo objects. So any star-like or planet-like object in the halo, the outer regions of a galaxy. So not just a soup of particles, but a real gravity-bound astronomical object. We've already ruled out most stars because they would be too bright. The main sequence stars and the giants. But some special forms of stars, like neutron stars or white dwarfs or black holes, might be dim enough to act as dark matter. And the same goes for planets, especially brown dwarfs, supergas giants that are just barely too small for fusion to kick in. And several large-scale experiments were run in the 90s and zeros to find objects just like these, using an effect called microlensing. Normally, light from a distant object would reach us like this. However, when there is a massive object, like a MACHO, in the way, the light is bent around it and more light is focused towards us, just like with a magnifying lens. This leads to a brief spike in brightness that can be observed and tracked. And you might say, okay, cool in principle, but how likely is that to happen? Well, not very. For example, when watching the Magellanic Cloud, a dwarf galaxy close to the Milky Way, we can only expect about 1 in a million stars to be lensed at any given moment. Well, the thing is, there are tens of millions of stars in this cloud, so when we just keep observing it for a couple of years, we should be able to watch hundreds of those microlensing events. But alas, all the groups performing these observations did not find hundreds of these events, but just a couple. And this small number is to be expected with just the known objects in the galaxies. We do not need MACHOs to explain that. So the whole MACHO idea is now, if not completely debunked, then at least extremely unlikely. Alright, so dark matter does not seem to be compact objects, but it might still be a large number of microscopic particles. And this hypothesis has been abbreviated to WIMP, weakly interacting massive particle. For those hypothetical particles to behave like dark matter, they'd have to have the following properties. They need to be stable, electrically neutral, massive, slow-moving, and only interact through gravity and possibly the weak force as well. Looking at all the particles we know, the standard model of particle physics, we have nothing that fits this description perfectly. Most particles and composite particles are unstable and decay after just fractions of a second. The only candidate from the standard model that was in the race for at least a while were the neutrinos. But their mass seems to be too low and they move too fast to fit our models of galaxy formation through dark matter. So what do physicists do when they have an effect but no particle to account for it? They invent a new particle. And incidentally, about at the same time where the dark matter problem was taken more serious, the concept of supersymmetry was also being developed. This is a hypothetical additional symmetry that proposes a supersymmetric partner particle for all known particles, a new fermion for each boson and a new boson for each fermion. While these models cannot make clear and concrete predictions, one forecast with reasonable assumptions was that the superpartners were at a higher mass scale and that the lightest superpartner, something called the neutralino, could be stable and in the 100 GeV mass range. And this would be an excellent explanation for the dark matter problem, so this seemed to be much more than just a coincidence. The obvious problem with something that has almost no interaction with regular matter, of course, is that this means it's almost impossible to find. All the experiments trying to find WIMPs need to be heavily shielded, buried deep underground and have to run for years on end. Absent a clear prediction of what exactly to look for, experimenters have to tune out everything they know and look for anything unknown that remains. but this means you just get an unknown signal and not that this is necessarily due to WIMPs. Many of those experiments are based on a hypothetical pair annihilation of WIMPs, which goes like this. WIMPs would conceivably annihilate with their antiparticles, just like regular particles do. This would create a number of particles of lower mass, so regular particles that we could detect. One example of this is the Fermi Gamma Ray Space Telescope launched in 2008. The basic idea was to look for unexplained signals from regions where a lot of dark matter is concentrated. And indeed, Fermi did detect a large amount of unexplained gamma radiation from the center of the Milky Way. The thing with unexplained signals is, though, that they may be explained over time. And Fermi's signals could all be explained by regular astrophysical objects like pulsars years later. Another interesting approach was taken by the Dama Libra experiment. According to models, dark matter on average rests with respect to the galaxies, so the Sun would be constantly moving through it, and Earth on its orbit around the Sun would be moving through dark matter at different speeds throughout the year. Hence, the approach of Dama Libra was to measure the same weak signals as any other experiment does, but also to track how these signals fluctuate over the years. And that is exactly what they got, a periodic signal repeating each year. While this is a very interesting result, it is still being discussed if there isn't a natural effect on Earth to account for it. Because up to date, no other experiment could replicate these results. Finally, as the supersymmetric particles are conjectured to be in the 100 GeV mass range, that means we should be able to produce them directly in the LHC at CERN. In fact, looking for these hypothetical supersymmetrical particles was one of the motivations to build the LHC in the first place. However, up until today, after 15 years of operation, not a hint of supersymmetric particles was found at CERN. And that doesn't just kick up the can to higher energies. Because for supersymmetric particles to have all the desired properties of dark matter, they would have to fall within this 100 GeV range. So even if supersymmetric particles existed at higher energies, they would not be an explanation for dark matter anymore. To date, no experiment has found any clear-cut smoking gun result of finding WIMPs. Some signals were reported, but they could always be explained by another source or could not be replicated. Such a null result in science is not a failure though, because it tells us what we can exclude. For example, look at this graph. It basically shows the relation between the mass of WIMPs and the likelihood of interacting with normal matter, but that isn't important here. The relevant point is that the colored areas are allowed by theory, and the curves are the constraints that follow from null results of experiments. This tells us where WIMPs can't be and where to look next, until eventually either something is found or everything is ruled out. And of course, constantly finding null results just to exclude some more areas becomes tedious over time, but that's the grind of scientific research. Hopes to find dark matter certainly were much higher at the beginning of the century, especially as the supersymmetry predictions were so promising, but here we are. It wouldn't be the biggest problem in physics if it were easy to solve. Also, it's quite likely at this point that whatever the solution to the dark matter problem will be, it will entail new physics. And that's what physicists are always looking forward to.